To continue our conversation about curve sketching and our summary of curve sketching, we have one more type of asymptote to talk about. So we spent a lot of time talking about the horizontal and the vertical asymptotes of a graph and how to find them. But now we're going to go ahead and take a look at what is called a slant asymptote. So a slant asymptote is an asymptote that behaves, is a function that behaves like a line, y equals mx plus b, and we call y equals mx plus b the slant asymptote of the curve of the function if, as we approach both positive and negative infinity, if we were to take away that slant asymptote, so f of x minus mx plus b, we get 0. Okay? So what that means graphically is that the function behaves like that line at the tail ends, at the infinities. As x is growing without bound, as x is decreasing without bound, the function is getting infinitely close. There is essentially no distance between f of x and that line. So what would that look like? And we'll come back and talk about that rational function in just a second. So what would that look like? Well, slant could look like a lot of different things, but let's just draw a couple little examples. That's a terrible line. Let's draw a couple different examples of visually what a slant asymptote might look like. So a slant asymptote is a line, y equals mx plus b. So I'm going to draw it I'm drawing a positive slope line here. And we could have something that looks like this. We could have the line doing something like this. That would be a function. Let's call this y equals f of x. That would be a function that as x is approaching infinity, as we head this direction, and as x approaches negative infinity, this function is starting to behave just like this line. If we were to continue to expand the graph out, the distance between this line, the vertical distance between the line and the function at both sides, is approaching 0. So that would be one example. You can have slant asymptotes combined with any other variation on a curve. So obviously, well, real quick, what you cannot have is a slant asymptote and a horizontal asymptote, because you've got your slant asymptote, your function is actually going to be approaching not a horizontal line, but a slanted line. We're assuming that the slope is not 0, that we don't have a horizontal line. That would then become just a horizontal asymptote. But you could have, say, a vertical asymptote. I'm going to make this one have a vertical asymptote. We'll just do one vertical asymptote on this one. And why don't we make our slant asymptote, even make it just go through the origin. And we've got a slant. So notice we've got a slant. And we have our vertical asymptote, and we could have a graph that is doing something like this. You know, it's got that vertical asymptote at 0. But as x is both increasing and decreasing without bound, heading towards along the x-axis to the two ends of the graph, the function itself is starting to behave like this slant. So it doesn't really have much to do, you know, the slant asymptotes don't have a whole lot to do with what's happening right in the center of the graph, I guess near relative, but near the origin. So the slant asymptotes, just like the horizontal asymptotes, really are discussing what is happening as x is both growing without bound and excuse me, decreasing without bound. I don't know, I guess we could do, let's just do one more quick example. So here would be an example where let's just throw in 2 vertical asymptotes and a slant asymptote. And we could have some kind of behavior like this, like we could be doing something like that, and then maybe we have, again, the slant asymptote, even though I dashed it out in here, you know, it's really irrelevant to the center of the graph, so you don't, I mean, you often have to draw it in to get the slope correct and all of that, but again, the function is being driven by other quantities near the origin. It's being driven by, you know, it's being bounded by its vertical asymptotes and so forth. So there would be another example. So again, what's happening as we approach the two ends of the graph is the function itself is approaching this slant line. It's behaving just like a line as x both decreases and increases without bound. Okay, so those are some visuals, but now let's talk about the mechanics of actually finding these slant asymptotes. And we are going to explore them as they relate to rational functions. So for a rational function, very specific types of rational functions will have these slant asymptotes, will have this behavior. And those are the rational functions where the degree of the numerator is exactly one more than the degree of the denominator. So where the degree of the numerator is exactly one more. So if you have, say, let's just look at these two examples that I have here. So this first one, you've got x cubed plus 4 divided by x squared. So notice that that rational function, the degree in the numerator is 3, and the degree in the denominator is degree 2. Since this is a rational function, there's no roots, nothing else, it's just a ratio of two polynomials, definition of a rational function. This will have a slant asymptote. And similarly, and this is the one we're going to do in just a minute, similarly here, when you look at the degree of this function, you've got degree 2, you've got a quadratic divided by a linear function. That is exactly one more, and so that means that we will have a slant. Okay. Okay, well, how do we figure it out? So, okay, so now we know which candidates for rational functions will have slant asymptotes. How do we actually find them? Well, what we do is we actually use long division of polynomials. So that goes back to some pre-calculus, and we'll go through that with this example that I want to do here on the video. So let's go ahead and get started. In the example, I'll review that long division. Okay, so here is the function that we just determined would have a slant asymptote, but I want to actually go through the entire process. I want to review that process again, the entire process of curve sketching for a function like this, for a function that actually will have a slant asymptote. So let's go ahead and start it from the beginning. I just took the brief summary here. I wrote out steps for curve sketching. The first thing we want to do is we want to find the domain. So when we're doing this and we want to find the domain, when we're looking at a rational function, what we need to be concerned about is if the denominator can be equal to 0. So notice on this case that x minus 2 cannot equal 0, so x cannot equal 2, which gives me a domain. Everything else is acceptable, but that x equals 2 creates division by 0, right? That's what the issue is. And so we have to say that the domain is from negative infinity to 2, and then from 2 to infinity. So that is our domain. So the domain is broken by that one point. Now, that's also going to, while we're in the midst of talking about that point, it's because that creates division by 0, it's a vertical asymptote potential. So I'll put a little question mark, vertical asymptote at x equals 2. We would need to double check to make sure that it is not also it is not also a root of the numerator. So it's not also going to make the numerator equal to 0. And so to do that, we could just quickly plug in 2 right here, and we'd get 1 plus 10 minus 4 times 2 is 8 over 0. So this is at x equals 2. Let's see what happens. Then that would end up being obviously not a 0 over 0, it's a 3 over 0, which means we have infinite behavior. Now we could examine which side of 2 approaches positive infinity and negative infinity and all of that, but right now we can definitely say, we can get rid of this question mark, and we can definitely say yes. Okay, this infinite behavior, knowing that this is going to be, you know, positive or negative infinity, that part I don't know without doing more work, and I'm not going to spend that time right now. But we do know that there's infinite behavior, which means it must be a vertical asymptote. Okay, that comes in a couple of steps. That's actually step 4 to determine all the asymptotes. But right now, when we're in the domain section, certainly for rational functions, it's worth considering those vertical asymptotes, because we're going to have breaks in the domain at those places. So we need to maybe take a pause right there and just finish out the vertical asymptotes. So we know we've got vertical asymptote at x equals 2. We'll fill that in when we get to the asymptotes. The second piece that we're going to want to look at is the intercepts. So let's go ahead and determine the intercepts of this graph. And I'm going to change that to black because that is our work for that step for the domain. So the intercepts. So if we wanted to find the y-intercept, I mentioned this when I went through the steps in detail. The y-intercept is often a fairly easy one if it exists to find. And so the y-intercept is when x equals 0. So when x equals 0, y would be equal to, in this case, 1 over negative 2, or negative 1/2. So the y-intercept is at 0, negative 1/2. Now the x-intercepts are when y equals 0, and sometimes they're easy to find if they exist. Sometimes they're not. Sometimes we would have to use some estimation techniques or a variety of other methods, but if they're too difficult when we're doing curve sketching, if they're too difficult to really pinpoint the x-intercepts, what I would suggest is that find the y-intercept. If the x-intercepts are easy enough to find, go for it. If you're going to end up spending too much time or going into estimation techniques for these, then you can just estimate after you get all the rest. You're going to have so much information after we go through this whole process that you'll be able to get good enough with our intervals of increase, decrease, concavity, inflection points, all of that. Once all that's in, we'll have good enough estimation for the x-intercepts if needed. Okay, so y equals 0. This happens to be a case, all of that. This guy happens to be a case where it's not going to be too hard if they exist to find. So let's see what I mean by that. Because it's just a rational function, and a rational function equals 0 when the numerator equals 0. So when that numerator equals 0, that's a quadratic. Could write it in descending order if we wanted to. That is a quadratic. It is not factorable, but that's okay. Quadratics, we should be real comfortable with quadratics at this point in calculus. So we can just go to the quadratic formula. Since it doesn't factor, doesn't look like completing the square is going to be all that easy, it'll turn into fractions. So let's just go to the quadratic formula. And negative b plus or minus b squared minus 4ac all over 2a negative 5 plus or minus, let's see, 25 plus 8, so that's going to be 33 over negative 4, and those are our exact answers. I did estimate these because we are going to use these to graph, and so these are approximately, at just using the calculator, negative 0.19 and rounding to 2 decimals, and 2.69. So that's what I got for those two intercepts, so 2x intercepts. So when y equals 0, the intercepts are at negative 0.190 and at 2.690. And let's highlight those pieces. So those are going to give me 3 ordered pairs that I can use for this plotting. And we had the domain up here. So this was the domain. So we've got the domain, we've got the intercepts. We could talk about, this is clearly not a periodic function, it's a rational function, it's not going to be periodic, but it's worth kind of thinking for a second about symmetry. Every once in a while we get an even or an odd function, and again, if it's something that's obvious and easy to show, we would want to do that. So take a moment, pause for a moment, and think about symmetry. And on symmetry, what you want to do is you want to think about what is f of negative x. And does that happen to be f of x or negative f of x, right? Like that's what we want to think about when we think about symmetry. So we think about f of negative x, but I do a quick little examination on this, and I notice by plugging in negative x here, I'm going to get negative 5x minus 2x squared right away in the top because I have an odd power and an even power in the top. There's not going to be any obvious symmetry. So nope. No obvious symmetry here, and we can move on. So let's move on into our asymptotes. Now, we already did some of the work for the asymptotes, so I'm going to go ahead and just capture that. We know that there is a vertical asymptote at x equals 2. Okay? That work was done when we did the domain. There are no horizontal asymptotes, but there is a slant asymptote, because the degree of the numerator is exactly one more. Now, we talked about this when we were defining slant asymptotes at the beginning of this video, but because the degree of the numerator is exactly one higher than the degree of the denominator, that is going to give us a slant asymptote. Okay? So there is a slant asymptote. So we have to figure out what it is. So how do we figure out what it is? Well, this is where we're going to review a little bit of polynomial long division. So let's come off to the side here and let's do some polynomial long division. I know you guys all remember that. It's like, oh yes, that was a fun little algebra 2 exercise. But remember it or not, we're going to have it come back right now. So to do polynomial long division, it's very similar to long division of numbers. So if we're going to do polynomial long division, we set up a long division problem. We're taking x minus 2 and dividing that into the polynomial on the top. The polynomial on the top, when it was given to us, I'm looking up in the upper corner here of the screen. When it was given to us, it was not in descending order, it was actually in ascending order. So I'm going to rewrite it as negative 2x squared plus 5x plus 1. So I can do the polynomial long division. And then we start to work this just like we work a long division problem. What we do is we look at the first term here, x, and we look at the negative 2x squared, and we say, what would I have to multiply x by to get negative 2x squared? Well, that would be a negative 2x, and then I multiply that by both of these terms, line them up with the corresponding terms here, and subtract, just very much like you would do with numbers, except we have polynomials with multiple terms. So hopefully it'll come back quickly. So this is going to give me a negative 2x squared here, and then a positive 4x, negative 2x times negative 2. Then I'm going to subtract, just like you would at this stage with numbers doing long division. So we subtract. When we subtract, these two terms cancel. When we subtract 5x minus 4x, we get simply x, and we drag down the next term. And then we repeat the process. So then we say, what would I multiply x by to get just x? And that would be 1. So I have a plus 1 here. 1 times x is x. 1 times negative 2 is negative 2. I now subtract. And I continue this process until, notice right here, those cancel, and then we're subtracting, and I get 3. I continue this process until the difference here is less than in degree the lead term that we're using here on the x minus 2. So I can no longer continue the division because obviously x doesn't go into 3 is another way to think of it. So what that means is that y, which was negative 2x squared plus 5x plus 1, just reordered that numerator, divided by x minus 2 is actually equivalent through polynomial long division to negative 2x plus 1 plus the remainder divided by x minus 2. Okay, so we use that to rewrite. So we rewrite. And notice as we take, if we were to want to look at the limit as x is approaching both positive and negative infinity of y, this is why polynomial long division works, we would simply be taking the limit as x is approaching positive or negative infinity of negative 2x plus 1 plus 3 over x minus 2. And notice as x is approaching infinity or negative infinity, this term goes to 0, and the function is going to behave like negative 2x plus 1. That is my slant asymptote. Now, of course, we would still have that limit in there. I should write that limit as x approaches positive or negative infinity. But the function itself, as we approach infinity, essentially becomes this line, or acts just like that line, because this other term here went to 0. So we have now found our slant asymptote. So we have a slant asymptote, and we can use that on the graph. So we have a slant asymptote of y equals negative 2x plus 1. So we've got a vertical asymptote, and we have a slant asymptote. Okay, Now we need to take derivatives and figure out where we're increasing, decreasing, and where we're concave up, concave down. So let's go ahead and do that on the next line. So for the fifth step, we need to figure out increase, decrease, and look at y prime. Okay, y sine of y prime. So let's go ahead and do that with the derivative. So y prime is equal to, we got to use quotient rules, so we're going to have negative 4x plus 5 times x minus 2 minus the derivative of the bottom is 1 times the top, negative 2x squared plus 5x plus 1, all divided by the bottom x minus 2 quantity squared. And I'm going to need to zoom in so I don't make any mistakes with my algebra here. So let's go ahead. We got to get this thing simplified. We got to figure out where the critical points are and then create a sign chart. So definitely don't want to do it in this form. I want to get this as simplified as possible. So we've got negative 4x squared plus 8x plus 5x minus 10 plus 2x squared minus 5x minus 1 all over x minus 2 quantity squared. And then in the numerator, I get a negative 2x squared plus 8x minus 11 all over x minus 2 quantity squared. So there's my derivative. So let's go ahead and find our critical points. So where does y prime of x equals 0? Where is y prime undefined? Y prime is undefined at x equals 2. Now the function itself is also not defined there, so I'm going to circle that. That is a vertical. We already know that's at the vertical asymptote. So, but we will want to use that because we could have change in increase, decrease at that point. So we'll want to put that on our sign chart. But remember that we've already identified that as an actual vertical asymptote. So now let's go ahead. When would it be equal to 0? Well, it's going to be equal to 0 when the numerator equals 0. So when negative 2x squared plus 8x minus 11 equals 0. That's a quadratic, not looking good on the factoring front. Yeah, that's definitely not going to factor. So let's go ahead, throw that into the quadratic formula, see if we get any roots out there. And x would be negative 8 plus or minus the square root of 64 minus 4ac all over 2 times a. And that's going to give me, let's see, negative 8 plus or minus the square root of 64 minus 88 over a negative 4. Not real. So we've got negative 8 plus or minus the square root of negative 24 over negative 4. So it's definitely not real. So we don't get any critical points from this point. So there's no places where the derivative equals 0. So we really only have that one vertical asymptote, but we do want to test on either side to see what's happening with the derivative. So we want to think about what is the sign of the derivative on either side of x equals 2. So we know that it's a vertical asymptote, so on my sign chart I'm going to identify that. It's not a horizontal tangent, it's not going to be a max or a min, but it's a vertical asymptote and we could have different behavior on either side. So let's just take some points. Notice the denominator is always positive. So let's do a couple test points. Denominator's positive there, but we could think about what's happening in the numerator. So if I were to plug in, say, 0 in the top, I can see that the numerator would be negative, and a negative divided by a positive will result in a negative. So it's going to be decreasing. And then we could test something on the other side, plug in something like, it doesn't even matter, we could plug in something like 10, and we'd get a negative 200 plus 80 minus 11. That's definitely going to be negative there as well. Negative divided by something that's always positive is negative. And so it's going to be decreasing. So this function is decreasing across its domain. So that means it decreases from negative infinity to 2, and then it continues to decrease on the other side of that vertical asymptote from 2 to infinity. Okay, so one last piece to do here, and that is to find the second derivative. So now we want to find the second derivative, and the second derivative we're going to use for concavity and inflection points. So we need the signs of the second derivative. So let's see, where's our first derivative? Let's keep that on the page here. So the second derivative is again, we're going to have to apply quotient rule, and we're going to apply it to that function. So that's going to be a negative 4x plus 8 times the bottom x minus 2 squared minus 2 times x minus 2 to the first times 1 times negative 2x squared plus 8x minus 11. And that's all over x minus 2 squared squared. So x minus 2 to the fourth. Okay, and again, I'm going to zoom in so that I can simplify that. So the first thing I notice is that I can pull out a negative 4 from here, which would make that negative 4. Let's actually do it in red. Negative 4, and then that would leave me with an x minus 2. So I can pull out a common factor of negative 2x minus 2 from both of the terms in the numerator. So I'm going to do that because I do definitely want to get this simplified so I can find those second order critical points. Doing that will leave me behind with a positive 2. And then actually I'll still have 2 of these x minus 2's. So x minus 2 squared. And then I pulled out a negative 2x minus 2, so I'll have a positive 1, I guess, technically, times negative 2x squared plus 8x minus 11. And then let's go ahead and finish simplifying, expanding the top out there, but we can cancel one of these x minus 2's, make that just to the third power. So in the top I have negative 2 times, well, let's see, this right here, x minus 2, when I square it, becomes x squared minus 4x plus 4. So I'm going to distribute the 2 to that. So I have 2x squared minus 8x plus 8. And then I can distribute the 1 or just drop the parentheses actually. Minus 2x squared plus 8x minus 11. And so what ends up happening here nicely in the numerators are those drop off, those drop off. I've got 8 minus 11, which is a negative 3. Oops, forgot my denominator, x minus 2 cubed. And that ends up being, this whole thing in the top is a negative 3. So in the top we get a negative 2 times a negative 3. So I actually get 6 over x minus 2 cubed. So a lot of work there algebraically once we used the quotient rule to find the derivative, but we got it simplified down to a really simple second derivative. And the second order critical points out of this second derivative there's no places where, so y double prime equals 0, that never happens. There's no place where the second derivative equals 0. Y double prime of x is undefined when x is equal to 2, but again, that's that place where we know we've got that vertical asymptote. So we already know that. We know it's a vertical asymptote, but again, still when we're looking at sign charts, we want to include those places because those are places where the concavity could change. So let's get our, we only have that one critical point that we know is a vertical asymptote. The sign of the second derivative, if I were to pick something to the left of 2 like 0, plug that in, it's going to be, obviously 6 is always positive, but then when I plug in 0, negative 2 cubed is negative, so that's a negative result here, which means we're concave down. And if I pick something like 5 and plug it in, I'm going to get a positive. 6 is always positive, and positive on the bottom too, because 3 cubed would be positive. And that will give me a positive result, so we will be concave up. So we know that we're concave down to the left of that vertical asymptote and concave up on the right of that vertical asymptote. Okay, we now have a load of information about the function, and we can take all of that and we can put it together and get a nice little graph. And so I'm going to try to get it all on the screen so that we can do that. It's going to be kind of hard, actually. There's a lot of information. So let's put our graph. Let's put our graph down here. So we've got our graph, vertical. Horizontal line. And the first thing we're going to do is I'm going to go ahead and draw in the asymptotes, and then we can plot some ordered pairs. I'm going to have to zoom in here so that I can get this graph, but let's let's go ahead and graph the asymptote at 2. We know, I should have kept my ruler out. We know we have a vertical asymptote at 2. So I'm going to just dash that in. I'm going to dash in my asymptotes with red lines here. And then we also know we have a slant asymptote at y equals negative 2x plus 1. So going through 1 and then with a slope of negative 2. So we know we're going to go through 1 on the graph and then we're going to have a slope of negative 2. So we're going to have a slant asymptote that is going to be crossing through the graph. Oh shoot, my ruler didn't stay with my graph. I was going to say I'm going to try to go out a little bit further there. I think we'll just scooch that up and then move this in so that I can get that to go. I want it to go a little bit further down the graph because it's really what's happening at the infinities. Okay. So now we have kind of the skeletons, the bones of the graph, and we can start to fill in the rest of it. And so we did have some ordered pairs here. So we knew that we had 0, negative 1/2 was a, let's see here if I can bring those points down. We did know that these points were points on the graph. Those were our intercepts on the graph. So let's go ahead and plot those. So at 0, negative 1/2, and at negative point, so negative 0.2 about, so in there, and at 2.69, okay, so we've got those ordered pairs. So these were intercepts. We also know, if I can scroll over a little bit, we also know a little bit, let's get the sign charts on here. We also know that we are decreasing across the entire number line, but we do have that vertical asymptote. So obviously we aren't continuous. We're going to have to jump over that vertical asymptote. And then we know that we're concave down on the left side of that vertical asymptote and concave up on the right side. So knowing the behavior of the function must behave like this slant asymptote and be decreasing means I must have a shape like this. So it must be doing something like that. And then it must behave over here on this side of the graph. It must also behave like its slant asymptote as we get larger and larger and larger. And so we must be coming up from this slant asymptote, hitting that intercept, and then getting close to that vertical asymptote. So we know we must be coming from the right side of the graph that we're going to look like that. And this obviously is going to continue to get closer and closer to that vertical asymptote. So we get a graph that looks like that with those intercepts. Now on this particular one, I didn't make a little t-chart. A lot of times I make a t-chart, especially if we have maxes and mins. We do not have, notice here, note, I always have you label your maxes and mins, but note there are no max min points here, and there are no inflection points. So, I mean, obviously I didn't label anything. The points that I've labeled here are actually the intercepts of the graph. So the only plotted points I have are the intercepts of the graph. There was a change in concavity, but it occurred at a vertical asymptote. And there we have our graph. Kind of looks, given the scale, I guess it does sort of look, they almost look like I don't know, kind of a funny little shape with like arms, like a person with their arms up and they're, shouting, jumping in the air with their arms up and their legs, sprout, kind of like a little, I don't know, I'm visualizing a little person's head here, Anyways, kind of an interesting graph. And again, I didn't pull the graph in from Desmos on this one. I really wanted to spend the time, and I want you to spend the time to use this chapter as a summary chapter. The only new piece here, and it's not really new, it's just new to us. The only new piece here is that slant asymptote. So you have to review a little bit of pre-calc with the polynomial long division. But doing that, you'll find your slant asymptotes, and then you can use those just like we do the vertical and the horizontal asymptotes, sort of to lay down a skeleton for the graph and then fill in with all the other information.